All right, guys, 5-4 day 3. We have two more types of problems that I need to get you through. And this is day 3. They're harder than day 1, definitely. And notice I gave you like a full sheet of paper for each problem. Okay, deep breath, good attitude. Here we go. Ready? So the first one is kind of a neat problem. We've got a guy who has a boat and a pair of sneakers, and he needs to get across and down river as quickly as possible. So let's draw a river. So there's the river, and I got this man standing at point A. So here's point A, here's our man standing at point A. He needs to get across the river and down the river to reach point B. So we'll put B down here. The river is 3 kilometers wide. And point B is 8 kilometers downriver. So all this is 8. Here are his choices. Option 1, he could row his boat directly across the river to point C. So we're going to row straight here to C. Let's make a C there. So he could row directly across, get out of the boat, and run all the way to B. That's option number 1. Option number 2. He could row directly to B. Okay, so he could get in the boat and row a nice straight diagonal all the way to B. That's an option. That. And let's see. Can I label that? Yeah, I can label that. So we got a right angle. So we've got 8 squared plus 3 squared equals our diagonal squared. So it turns out that is radical 73. 64 plus 9. Yep, radical 73. Okay, so that's option number 2. Option number 3. He could row to some point between B and C. So he could row across somewhere in here. Somewhere. Stop, get out of the boat, and run the rest of the way. And that point would be called D. Those are his options. So, we know how fast he can row. We know how fast he can run. Let's basically look at the time for all 3 options. So, I know that distance equals rate times time. So time is equal to distance divided by rate. All right, option number 1. We're going from A to C to B. From A to C to B. Okay, so from A to C, the distance, hang on, time equals. From A to C, the distance is 3. From A to C, the distance is 3, and he's rowing. What is his rowing rate? His rowing rate is 6. So 3D divided by R plus, and then he has to run from here to here. Well, that distance is 8. And what is his running rate? His running rate is 8. Okay. So option number 1 is going to take him 1.5 hours. Okay. Option number 2. What if he rows from A directly to B? Time equals distance divided by rate. All right, so we figured out using Pythagorean theorem, this is his distance, this is his rate, got out my calculator. Okay, better. Option number 3. What if we go from A to D, which is kind of an unknown point, and then to B? Well, I need, now remember, this is unknown. With this, I drew it here, but it could be here, it could be here. We really don't know. It's unknown. We've got to work out the entire problem in order to figure that out. Where should this be? All right, so what is this distance right here? We can't lock in a distance, but we can write a representation of the distance. So I need to somehow represent this distance as well as this distance. And notice the question says, where should he land? Where should he land to get there as soon as possible? So I think maybe I want to call this x. You think that sounds like a good idea? Let's call this distance x. What am I going to put for this distance? Don't tell me why. It's all of this, which is 8, minus that. So right here, I'm going to write 8 minus x. Okay, good. We're getting somewhere. This is his running distance. So if he rows to here, he's going to get out and run this distance. That's good. We've got a good representation for his running distance. Now let's get a representation for his rowing distance. And you've got a cute little right triangle here to help you with that. So his rowing distance, I'll call it r for now. I can say r squared equals 3 squared plus x squared. So the square root of x squared plus 9, that's this distance right here. The square root of x squared plus 9. Okay, so in this third column that I've made in your notes, let's put a representation of time. So what's going to happen, he's going to row this distance at a rate of, I think it's 6. He's going to get out. He's going to run this distance at a rate of 8. Let's write that. His time equals the rowing at a rate of 6 plus the running at a rate of 8. Okay, and we don't know what this is. Like we can't get a number really quickly for time because we don't know where he's going to land. So all we've got is a representation. You know what we want to do though? We want the least amount of time. Right now, this one's the winner. I wonder if this one could be the winner. Least amount of time. Hey, let's minimize this function. Least amount of time. Let's minimize this function. As soon as possible. Minimize time. So, let's do a derivative on that equation. After you simplify it. So here I go. I'm going to simplify it with a derivative in mind. So I know I'm going to have to take a derivative. I think I'm going to write 1/6 x squared plus 9 to the 1/2, right? Don't you like that, knowing that you're getting ready to do a derivative on it? We're a coefficient of 1/6, put that to 1/2. And then I'm going to unadd these fractions together. So 8 over 8 is 1 minus, and then x over 8, I can write 1/8 x, right? So 8 over 8 is 1 minus x over 8, or since I'm getting ready to do a derivative, I just wrote it as 1/8 x. Okay? I think it's good. Let's do it. The derivative of time, and x is our variable, so I'm going to power rule. Lower it, chain rule. Derivative of 1 is 0 minus 1/8. Okay. I'm going to go ahead and set it equal to 0, and I'm going to simplify what I can. So 2 over 12, there's an x on top. There's a 6 and a radical on the bottom. Minus 1/8. Now, I said set it equal to 0. Think about this just real quick. Is there any way your derivative could blow up? Well, the only way your derivative is going to blow up is if you've got, like, if your denominator could be 0. Will this ever be 0? This will never be 0. Because whatever you plug in, you're going to square it, which turns it positive, and then you're going to add some more to it. So, no, that's never going to be 0. All right, so I think what I'm going to do is maybe move the 1/8 over and cross multiply. Does that sound like a good plan? 1/8. Now cross multiply. Couple of things. I need to square both sides, and I probably ought to get rid of the 6. I'm not sure what I want to do first. I think I'll go ahead and square both sides. Watch those algebra skills right there. Be careful when you're squaring. Be careful. Ooh. 324. Okay. Of course, I got two answers for that, but I only want the positive version. Okay, so that's, let's see, I think that's my answer to my, well, not yet. So, 3.402 kilometers downstream, what's that make his time? Like, should we just assume that it's the quickest? Or should we actually plug that back in and check? I think we should plug that back in and check. So if we take 3.402 and plug it in, of course, with a calculator, plug it in here and here, the time turns out to be 1.33 hours. And that is the quickest route. And that was a 16.5-minute long problem. Holy moly. All right, let's see if we can beat our time on this last one. Ready? We have a sideways parabola. Centered at the origin. And so there's the parabola, and we want it closest to the point 1, 4. 1, 4 is going to be up here. So here's what it's asking. Find the point on the parabola closest to this. Closest. I think we want to minimize something. We want it to be closest. We are looking for the minimum distance. We need to minimize distance. All right. So what that means is we need a distance equation. Holy moly. We need an equation for distance. Now, this looks awful. I can promise you it's not going to be like you're thinking, oh my gosh, I'm going to have to do a derivative on that. And yet you will. You will. But it's not going to be as bad as you think it's going to be. So, in my opinion, the hardest part is figuring out what do I plug in here before I do a derivative. I mean, obviously, I've got 2 different x's, 2 different y's. Basically, it's almost like I've got 4 different variables. You've got to narrow this down before you do a derivative. So in order to do distance, you need 2 points. In order to use distance formula, you need 2 distinct points. Do you have 2 distinct points? We have 1, the point 1, 4. Your other point comes from this parabola. So 1, 4 is obviously an ordered pair that we're going to use. 1, 4. That's a no-brainer. Your other point your other point comes from this equation. Now, let's look at it right here. Because I've got one of my variables isolated, okay? So let's look at this. Now think about this. If I were going to ask you to make a table Make a table of values. Here's what you would do. Which column would you fill first? Would you go like 0, 1, 2, 3? Would you make up your own x's? I don't think you would. You want to make up your own numbers for your input variable. This is your input variable. You would go 0, 1, 2, 3. Do you know what you would do to each of these numbers to get your x that goes with it? You would do 1/2 y squared, 1/2 y squared, 1/2 y squared, 1/2 y squared. That's what you would do to each number you plugged in. Whatever you plugged in, you would square it and multiply it by half. Plug in 0, square it, multiply it by half. Plug in 1, square it, multiply it by half. Plug in 2, square it, right? Okay. Look at this ordered pair. What are we plugging in? We're plugging in y's. That's our input variable. How do we get our x? We take this and we square it and we multiply it by a half. We take this, we square it, and we multiply it by a half. Look what I just did. I just created an ordered pair in one variable. This is my input. This is my output. I plug in y's. I do this math, and it gets me my x's. So, there you go. You've got this ordered pair and this ordered pair. Put those ordered pairs in your distance formula. Distance equals. All right, I've got subtract your x's. So I'm going to go 1/2 y squared minus 1. Subtract your y's. Okay? Grab my two x values. I grabbed my two x values, subtracted them, squared them. I grabbed my two y values, same order, subtracted them, squared them. Now, good news, bad news. The good news is we are kind of ready to do a derivative in that I am down to one variable. So I can do the derivative of distance with respect to y. That's good. The bad news is this is going to be an awful derivative to do. It's just going to be terrible. You've got this huge quantity to the 1/2 power. You'd have to power rule it, chain rule that. Just, oh, it's going to be bad. So here's a couple of things you can do. You can get rid of this radical by squaring both sides. Slight problem in doing that, although it's not a big deal. This is the name of your function. D is a messy function. Doing it the way it's written, I could write d prime or d, y, whatever. Okay, easy derivative. When I square both sides, this becomes d squared. Now all of a sudden, my d represents a messy function. And I'm going to have to use implicit differentiation. Not a big deal, but I just want to let you know that that's what we're doing. Okay, so here I go. Let's square both sides. I've got d squared equals no more radical, praise the Lord, 1/2 y squared minus 1 quantity squared plus y minus 4 quantity squared. Again, options. Just kind of think, just kind of think ahead and see what you would like to do. We can go ahead and do a derivative now, or you could multiply these out. This one would be totally easy to multiply out. This one would be kind of yucky. So think about foiling it and then doing a derivative on a polynomial versus chain ruling it, like power and chain. Either way, I don't know. I'm going to go ahead and start a derivative. Here I go. Ready? This is messy. This is messy squared. So I'm going to start with implicit differentiation. So I'm going to power rule it, 2D, chain rule it. Okay, I wouldn't get too angry if you wrote D prime. It's okay, whatever. All right, chain rule it equals, here I go. Power chain. Power chain. Let's see what we can do. Oh, well, first of all, how about this? There's a 2 there, and a 2 on this term, and a 2 on this term. You okay with me dividing everything by 2? Let's divide everything by 2. That'll make it a little bit better. All right, so that 2's gone. I can put my y in. And then I'll divide by D. Right? Divide everything by D. Okay. Set your derivative equal to 0. Check and see if it ever blows up. Well, yeah. So what's it going to take for this fraction to blow up? This distance would have to be 0. That distance is not going to be 0. From my parabola to my point, that's not going to be 0. So this derivative is never going to blow up. Is it ever going to equal 0? Yeah, I think it can. I think it can equal 0 if the top equals 0. So 0 equals 1/2 y cubed minus 4. 4 equals 1/2 y cubed. 8 equals y cubed. Y equals 2. Oh, I like that answer. Yeah, I like that answer. Y is 2. All right, bring it all the way back up here to the top. Y is 2. So what's x? Well, square it, multiply by 1/2. That's the point on the parabola. How do I know it's on the parabola? Because I plugged it into the parabola equation. It's on the parabola. That's the point on the parabola closest to the point 1, 4. All right, that was a lot of work, but notice that I went ahead and squared both sides to make my derivative better, and then it was our call whether or not to FOIL these out or not. Okay, be careful with that algebra.